All right, so interrupt me anytime. I sometimes forget and walk off the screen. Let me know that if you can't see something. And today's lecture then is a review of geometry that we're going to use in here. But you'll find early in the course when we discuss triangles, is that you can start the problem solving a triangle with trigonometry, but then to finish it is complicated trigonometry, and you can instead use these geometry principles. There are three major theorems that we want to discuss that will be used extensively throughout the semester in order to avoid doing the longer trigonometry method. The first one is the sum of angles theorem. And it says, very simply, the sum of the angle measures in any triangle is 180 degrees. All right, that should be very familiar. For example, if I give you a triangle like this, and I say, well, this one's 100 degrees, and this one's only 35 degrees, I wonder what that last one is. Let's just measure this angle alpha. You just say alpha, since these all add up to 180 degrees, is 180 minus the other ones, right? So I've got 45 degrees left. Angle measures work like this. A rotation, I'll refer to. Mostly what we're getting at today is review of these three basic theorems, but also a lot of terminology. So one rotation will be 360 degrees. Then, if we take half a rotation, it ought to be half the measure if we're measuring equal increments here. So we'll call that 180 degrees, and we'll call that also a straight angle, because it follows a straight line. Now, if we take half of that, now we've got what's called a right angle. We'll say that's 90 degrees since it's half of this measure. And then there's some other very useful angles besides. I'll call those special angles. But we'll say more generally that the special angles are these and any multiples of them. Make sure I keep moving this over enough. We could take, for instance, we're doing half, half. We could do half again and say that's 45 degrees will be a special angle. Or we might break this right angle into three equal pieces, right? 90 divided by 3 leaves 30 for this one, and then twice that is 60 for this one. These will be special angles also. Those come up extensively in nature and in engineering and so forth, right? So we're going to refer to those as special angles and say also multiples of these are special. So then all these angles are special too. These are going to be angles that we can easily find trigonometric solutions for in triangles. Now we'll say also that two angles are supplementary if their sum is 180 degrees. That is, if they add up to a straight angle. Or they can be complementary if they sum to 90 degrees. All right, those come up in lots of important cases. For instance, this one, I have a straight line and I cut it. Maybe this is 35 degrees. I might say, what's the supplementary angle? Alpha. Well, since they add up to a straight angle, we simply say alpha is 180 minus 35 degrees. Gives me 145 degrees. Also in a right triangle, we have the following. A right triangle is a triangle that has a right angle in it, right? There's never more than one right angle, because if you have two of them, they add up to 180 degrees already. There's no degrees left for the last angle. The other two angles are then acute. They're less than 90 degrees. So 0 degrees less than the angle less than 90 degrees are complementary. They sum up to 90 degrees. And you can see why immediately, right? You draw a right triangle, and we'll make this little square bracket here to indicate a 90-degree angle. Let's call this one alpha and this one beta. We use small Greek letters commonly to measure angles. If the three add up to 180 and 90 are taken here, then the remaining two, alpha and beta, add up to 90 degrees. So I'll use that fact a lot during this semester. I'm going to start this. I should have started the sum of angles theorem that for any triangle, the three add up to 180. For a right triangle, the two acute angles add up to 90. So I'll mark these through the semester when I want you to memorize them. Right? So an easy thing that's going to come up when we're solving a triangle is I'll get all but one angle in an oblique triangle, a non-right triangle, or I'll get one a right angle and another angle, maybe that's 65 degrees, not drawn to proper proportions here. If these are going to, we can say alpha here, because these two are complementary, it's just 90 minus the other one. And so I'll write that down, right? And so that's 25 degrees. So there's angles in a triangle, the sum of angles theorem, and how it applies to general triangles and right triangles. The second thing from geometry we want to discuss is the Pythagorean theorem. This can be two. Unlike the sum of angles theorem, this only applies to right triangles, right? The other one applied to any triangle. And it says in a right triangle, and we draw it this way, is standard. We'll call the two legs A and B. The legs are the two sides that are not opposite the right angle. And hypotenuse, the side that is opposite the right angle, right? Over here. That'll be called C. The Pythagorean theorem. It's actually not hard to prove. It's kind of a fun, easy proof. You do just with pieces of cardboard, for instance. You find always that a squared plus b squared equals c squared. Right? So there's the Pythagorean theorem. But what I want to do for class, since we use this over and over and over, is this. We'll say the Pythagorean theorem solved for its sides is this. So don't let it confuse you when you see this. If c squared is a squared plus b squared, then I can square root this and say c is the square root of a squared plus b squared. There are actually two solutions to this, right? Like if some number is equal to 4, a squared is, say c squared is equal to 4, c could be plus or minus 2, but since we're talking about lengths of sides, we'll say c has to be the positive number that has this squared. C squared is this, so c must be its square root. So there is the Pythagorean theorem solved for c, is what I'll call that. Similarly, if I take this and subtract a squared over, so that I have b squared equals c squared minus a squared, I can square root that, and I find out that b is actually the square root of c squared minus a squared. And similarly, by subtracting b squared over, I have a squared equals c squared minus b squared. Square root that, and I find out that a is the square root of c squared minus b squared. So you subtract to get a leg, you add to get the hypotenuse. I will use those frequently, call them the Pythagorean theorem solved for its sides. So don't let that throw you when I do it. Now with all that info, we can start to ask some more interesting questions. There's a bunch of them. Here I've printed off the homework supplement on some colored paper. And the geometry review is in the first part of this. And we can ask some questions like this on the Pythagorean theorem and on the angles that we have here. Find the measure in degrees. We will do radians shortly for those of you who've seen that before. Of 1/3 rotation. How about that? What is 1/3 of a rotation? I have a fraction of the way I go around the whole circle. All I have to do is say the angle, let's call it theta, is 1/3 of a rotation. But a rotation is 360 degrees, so it's 1/3 times 360 degrees. Remember how to multiply these things. If you multiply a fraction times a whole number, you just write the whole number as 360. Such as 360 is 360 over 1. You take top times top over bottom times bottom. I'm just reviewing algebra rules. And this is 360 over 3. It's 120 degrees is 1/3 of 360, right? There's the angle measure for a fractional rotation. You just multiply 360 degrees times the fraction, right? So the harder one now is, suppose I now want 7/12 of a rotation. How about that one? What's the measure of 7/12 of rotation? You just take 7/12 times 360 degrees, right? Gives you 7/12 of 360 degrees. And now you say, well, here's my fractions again, top times top over bottom times bottom, right? This is a fraction also. 7 times 360 degrees, and this is what I'm talking about remembering your algebra. Over 12 times 1, I'll just write 12. How do you reduce the fractions? On the test, I want you to always simplify these. For this class, you need to have a calculator that has trigonometry on it. Here's the TI-84. I present this one because a lot of you probably got it in high school. Some of these calculators will reduce your fractions for you. I don't think this one does, but you're welcome to buy one that does. I can't check that on the web anyway. That will help you with this, but you want to be able to do these by hand anyway. Instead of multiplying this out, I'm going to first factor this and cancel any common factors. So I'm going to call this, or at least I'll partly factor it. I'll say that.
Could you turn the camera just a little bit? Half of what you just did is cut out of the screen.
It's off. Is that better?
Yes.
Okay, thank you. Looked like it was on here. Thank you very much. So I'll say actually 360. Sometimes this is hard to do it all at once, but if you remember, 12 goes into 36 3 times, and then there's a 0 hanging on. You can say this is 3 times 120. Well, let's call it 30 times 12 divided by 12, and I can cancel the 12. And now I've got 7 times 30. This apparently comes out to be 210 degrees. Wait a minute. Yeah. It's not right. Huh. Yeah, okay. So there's finding angle measure when you have a fraction of a rotation. Just by way of reminder again. Please do come to class either online or in person once we're able to meet in person. I think you'll find you'll pick up a whole lot of things here that are small like that, like reducing quotients. And here's the kind of thing we can do too. Find the angle measures shown in this diagram. Now I have a right angle here. It's marked with this sign. And suppose I have here, let me make sure I'm reading this right. Three x plus 4, we don't know what x is. Another angle measure here, x plus 4. So how do I find out the angle measures? I can say, well, these are complementary angles. Evidently 3x plus 4 and x plus 4 add up to 90 degrees. So we combine in algebra the like terms. 3x and x makes 4x. 4 and 4 makes 8. And these really should have had degree symbols on them. They just aren't on the handout. And now you subtract, again, you combine these like terms, 8 degrees and 90 degrees. Combine the things with x, combine the things without x. Right, the 4x equals 82 degrees. And then you can divide that by 4 and get that x equals 20.5. Let's put it 82 over 4 degrees. That answer is a point off on the exam because you didn't reduce it, right? What you want to do is cancel the common factors out. So once again, from algebra, every number, this is a fundamental theorem of algebra, every whole number bigger than or equal to 1 factors uniquely as a product of prime numbers, numbers that are divisible only by 1 of themselves, and up to reordering those. So we can factor 82 actually as twice 41, and then 41 isn't divisible any further. We can factor 4 as 2 times 2, and then we say, oh, look, we can cancel these 2's. So the better answer, the one you will get credit for on the test, is 41 halves degrees. This is an exact answer. I'd like you to leave your answers exact. However, in this case, since the fraction has a terminating decimal representation, we can call this 20.5 degrees, and I'll also give you credit for that since it's exact. If it starts becoming a fraction whose quotient in decimal form goes on forever, then leave it as a fraction. Don't write the decimal, because once you round it, it's not exact anymore. So for exact answer, either of these are okay in this case because this one's terminating, but in general, you want to write the fraction. Now that's x. I was asked to find the angle measure, so 3x plus 4, we can call that angle alpha. 3x plus 4 degrees is then 3 times 20.5 degrees plus 4 degrees. Let's see, 61.5 and 4 is 65.5. And then the other angle, x plus 4.
I'm sorry, but the camera, we can't see that.
Yeah, I was worried I was getting it at the end. Thank you.
Thank you.
So this one comes out to be 24.5. Now it might be a good idea to check that they add up to 90, and sure enough they do. My best students almost always check their answers when they're done, and when they do, they often do better in the test than I do, and I don't check my answers. So make sure on the test when you have a little extra time, check your answers at the end by seeing they add up to 90 still. So there's this kind of problem using complementary angles. Now for the Pythagorean theorem, there's a few problems in here also. Suppose I gave you this kind of a problem. Suppose I said this side is 8, this side is 12. I wonder what this side is, right? Since it's a right triangle, the Pythagorean theorem applies. So we'll use the Pythagorean theorem to solve for a, which is a equals square root of 12 squared minus 8 squared, right? C squared minus b squared. Pythagorean theorem. Well, this is 144 minus 64. So let's see, it's square root of 80. That's a wrong answer on the test too, right? It's not a big deduction, but what am I not doing here? Not reducing my radical, right? I can rewrite this. 80 can be factored, right, uniquely as a product of primes up to reordering them. We can say, well, it's an even number, so some people like to make this factoring tree. You can kind of do this in your mind, though. It's 40 times 2, right, since it's an even number, divided by 2. Then 40 is even again, so I can say, well, that's 20 times 2. But 20 is 10 times 2, and then you can keep going like this. I still have more room. Try it again. And then finally, 10 is 5 times 2, and 5 and 2 are prime numbers divisible only by 1 of themselves. So you come down here and you say, this is the way 40 factors, 2 times 2 times 2 times 2 times 5. So there's actually 4 2's in here. I could call that 2 to the 4th or 4 squared times 5. And I'll say, well, the square root of the product of positive numbers or non-negative numbers is the product of the square roots. And square root of 4 squared is just 4, and I wind up with 4 square root of 5. When you write these products, a whole number times a radical that doesn't reduce, this is the radical sign, the root sign, you just leave it as the whole number first multiplying the radical. So there's the way I would like to see that answer on there, and that's the way the answers on the homework sheet will appear. Usually when you have a right triangle, because of this square root, you wind up with a number that has a square root still in it. I don't want to see the decimal on this form unless I say round your answer. This one might have said round your answer, I've forgotten now. Doesn't say that, so when I want an exact answer, leave it like this. With the radical, here's an interesting theorem. This is why I say come to class, because you learn things that are really useful later on, proofs and little tidbits that help you in your later classes that I really can't ask you in the test. But why don't we write this in decimal form? It's because of this. There's a theorem that says the square root of any whole number, which is a number with nothing, a non-negative number with nothing after the decimal point. One of these is called a whole number, 0, 1, 2, 3. The square root of any whole number is either again a whole number or a number that in decimal form goes on forever without a repeating pattern. So it's like pi, it goes on forever and you don't get a repetitious list. Unlike fractions, every fraction either has a repeating decimal or it might be in the special case a terminating decimal, like square root of I'm sorry, like 3/5 is 0.6. So that's a repeating pattern of 0. So every fraction has a repeating pattern. However, a square root either is a whole number or it just goes on forever without a repeating pattern. It's an interesting thing. So if you give me the decimal form of this, you have to round it somewhere. And once you do, it's not exact. Right? So exact answers, leave them as radicals, just reduce them as far as you can. Now, the third theorem we want to talk about is for similar triangles. We'll use these quite a lot. Two triangles are similar if they have the same three angles, which means they're the same shape. It's just one is the other one scaled up. So we could draw one like this, let's say, with angles alpha, beta, gamma. The convention is that opposite alpha, it's like the convention for right triangles. We'll mention in a minute. Angle alpha goes opposite A, angle beta goes opposite B, and angle gamma goes opposite C. In some textbooks, instead of using alpha, beta, and gamma Greek letters, these are small Greek letters here. Opposite alpha, they'll put point A and call that angle A. Opposite B, they'll put, A. Opposite B, they'll put point B and call that angle B, and they'll call this angle C. That's another convention. I'm not going to use that in this class, partly for the following reason. Now I have a similar triangle, so it looks just like that one, same shape, but bigger. It'll have angles alpha, beta, and gamma. I'll call this big A, big B, and big C. And what do we know about these? This one is just, this one's scaled up. And so what happens is, if this one is twice as long as this one, say, then this one will be twice as long as this one, and what you'll do is get the scale factor for each of these ratios. So C is to C, is B is to B, as A is to A, it's the same scale factor. So be aware of this property for similar triangles. This actually is the whole principle behind trigonometry, is this similar triangles property. But more than that, also, if you take, say, little a to little b, that's the same as the ratio of big A to big B, right? because each of these is just scaled by the same number. Some number may be k or something. So this is, oops, maybe little a is k times this one, and little b is k times this one, and then the k's cancel. They have the same ratio, they're the same proportions, right, in geometry. So we won't go through prove all these, but we'll just remind ourselves of them. Little a is to little c, and big A is to big C. They're in the same proportions. And little b is to little c, and big B is to big C. So there's these two standards for similar triangles. You can either compare corresponding sides, or you can correspond the same size in the two different triangles and have that. This actually comes up with an interesting way to sometimes avoid doing trigonometry. I'll give you a short problem here. This is like one of the homework problems actually, but it's a personal experience problem I like to portray. Comes up practically in lots of applications. Sometimes you see something, you want to know how big it is. How can you figure out how big it is? In my backyard, I had a tree years ago, a beautiful evergreen, and it got the mountain pine beetle in it, and it died. And I had to have it cut down before it fell down, right, and knocked the fence over or something. It's very tall. I didn't know how tall it was. I wanted to get an estimate, so I call them up, well, how tall is it? You know, that tells them what estimate to give me, but I didn't know, so I had to find out its height, but I don't want to climb all the way up there. It's very dangerous at the top. I can climb part way up, but what you can do is this. Can you see how to do this without the trigonometry? Like I showed you the task, you measure, pace off the distance, measure the angle, trigonometry configured. Here's how you can do it even just with similar triangles. If I take the shadow of the tree out here on a sunny day, there's my tree shadow, and I pace that off, right? I measure that, it's on the ground. We'll assume it's a right angle to the ground here. And suppose this is maybe 24 feet, right? And now I go over and stand here and set it so my shadow comes out to this tip here. Maybe this is 6 feet. I'm sorry, 9 feet. And so I'm about 6 feet tall, I already know. And so now what I can do is I have these similar triangles. I said that similar triangles are triangles that have all three angles equal. Actually, if you have two of them equal, then the sum of angles theorem forces both of the remaining angles to be the same measure so that the angles in each triangle add up to 180. So I can take that principle here and say this is the same angle because it's in both triangles, right? This one and this one. And then let's see, these are both right angles. That's a right angle because I'm standing straight up, and that's a right angle because the tree is. If two angles in the triangles are the same, then it follows that this one must be the same as this one, right? So I have similar triangles. Now I make a nice ratio. I'll say this side is to this side by the similar triangles theorem. H is to 24 as 6 is to 9. There we go. And I can solve that without even going to trigonometry by similar triangles. So now we multiply both sides by 24. This arrow means implies. It means if this is true, then this is true. I also like to draw double arrows, and those will mean this is true if and only if this is true. So this implies this, and this implies this. Is the way we write it. So we can write equivalent here, or in this case. I can multiply both sides by 24. The 24s will cancel on the left. I'll get h equals 24 times 6 ninths, right? And then once again, remember to multiply whole numbers times fractions. We just write them both as fractions. And I have 24 times 6 over 9. But wait, before I multiply that out, I'm going to first see if I can cancel something, right? 9 factors as 3 times 3, right? 6 factors as 3 times 2. 24, well, it's divisible by 2, so it's 2 times 12. And then 12 is 2 times 6, and 6 is 2 times 3. So there's my factoring tree in my head, if you like. I can cancel a 3 here, and a 3 here, a 3 here, and a 3 here. Evidently, I'm just left with 2, 4, 6, 8. I'm sorry, 2, 4, 8, 16. There we go. This one of my two, 16. So this tree would be 16 feet tall. My tree was actually taller than that, but they said it was gonna be $600 to cut it down. So I bought a chainsaw and went part way up and lopped it down in pieces. But there's how you can measure how tall things are in a distance. If you can just pace off the length to them. All right, so there's some applied problems from geometry. And here's one more. Again, please be able to do these. I may give you an extra credit problem here pretty soon, just to make sure we're keeping up. Here's another similar triangles problem. Suppose I drew you a figure like this. This is one of the homework problems I want you to look at. So if you had trouble with this one, take a look at what we did in class. And I say, this is A, B, C, D, and E. And in this triangle, this measures 15 feet. This is X, we don't know what it is. This measures 7 feet, this measures 11 feet. And I say, what is X? Find X to 2 decimal places. This time, this means round. So if I don't say round, I want an exact answer, leave it as a square root, leave it as a fraction, unless you can write it as a terminating decimal, that's okay too. But if I say put it to 2 decimal places, that means round. I can use similar triangles for the following reason, right? This big triangle and this little one share a common angle, so that's congruent to itself. Now we're given here, I didn't write it down, given that AB is parallel, the parallel symbol, to DE, we can say we have this property from geometry. Remember this, if you have 2 parallel lines, you cut it with another line, we call this a transversal. And when you cut it, 2 parallel lines with a transversal, then these angles called alternate interior angles, I'm sorry, they're not alternate interior, they're corresponding angles, are equal. Corresponding angles are equal. Also, this one is equal to this one. Those are called alternate interior angles. They're interior to the parallel lines and alternate sides of the transversal. So alternate interior angles are equal. Corresponding angles are equal. And then also this one and this one are equal. Alternate exterior angles, alternate sides of the transversal, exterior to the parallel lines. And so we have all those 4 are equal. And then this one, I'll put 2 hash marks, is supplementary to this, so it's 180 minus this one, and it also has its opposite angle and alternate exterior angle and corresponding angles equal. So when you have parallel lines, you have 4 of these angles congruent and the other 4 congruent, and you can figure out things like, well, these 2 parallels have these as corresponding angles, so they must be congruent. And similarly, these are corresponding angles. Oops, I should have put 2 on here. These are corresponding angles, so they must be congruent. Now we see we have similar triangles, right? With similar triangles, we have the following. This side of the large triangle, x plus 15 is its measure, corresponds to this side of the smaller triangle, 15. That should be the ratio, the same as the ratio of any other 2 corresponding sides, such as 11 to 7. So we can write this ratio down, right? Now, how do I solve this? Again, this is where you have to review your algebra. You have to know the fractions. You have to know how to solve these basic linear equations. Yeah, I can multiply both sides by 15 to get rid of the quotient over here and say this is x plus 15 equals 15 times 11/7. And let's see then, x equals 15. Right, we write this as a single fraction. 15 times 11 over 7. And now this is 165 sevenths, so x plus 15 is 165 over 7. But I've still got this 15 hanging on here, so I'm going to subtract it over. X equals 165 over 7 less 15. And how do I take care of that? Again, this is algebra. If you want to subtract two numbers, at least one of which is a fraction, you put them over a common denominator, right? So I'll write this as 165 over 7 minus, and I'll multiply this one top and bottom by 7. It's the same quotient. I can cancel these. Say 7 times 15 is 70 plus 35 is 185. Uh-oh, I got a mistake here, don't I? Let's see. Oh, I mismultiplied here, right? 15 times 11. That's all right.
That's right.
Okay, that's all right. Yeah, this is 85. Yeah, thank you. Okay, 85 over 7. Yeah, there we go. So what I have,
Actually, 15 times 7 is 105.
yeah, I can't multiply this morning, can I? Thank you. So yeah, 15 times 7, 70, and 35 is 105. Yeah, so I'll wind up with 67ths. There's an exact answer, but I didn't ask for an exact answer this time, right? You can do this on your calculator. And we'll bring out from that. Sevenths, unfortunately, has a repeating decimal that repeats every 7 decimal places. And so it goes on forever with a repeating pattern. I got 8.5714, blah, 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 right? And 2 decimal places, this is rounding, which we'll do all semester, means take 2 digits after the decimal point. Here's the first digit. The digits are the numbers 0 through 9. So I go over to here, and then if the next digit is 5 or greater, then I round this up to 8. But if the next digit is less than 5, like in this case, then I just keep it the same. So we'll say this is approximately equal to 8.57 when I round to 2 decimal places. All right, so we did fractions, and we did radicals, and we did rounding out of algebra. Later in the semester, I'm going to expect you to do factoring also is the other big thing, including the quadratic formula is a really useful thing for us. But you can see we have a little bit of algebra intensive material. Now, the next thing, there's an interesting applied problem I'll let you try here too. Next thing is to think about special triangles. These are angles that have triangles that have special angles in them. Couple interesting cases is an equilateral triangle. We'll probably not refer to this much, but this is an angle with a triangle with all 3 angles equal and all 3 corresponding sides therefore equal. So if the 3 angles have to add up to 180 and they're all equal, then 3 times the angle is 180. Each angle must be 60. Right? You put 3x equals 180 degrees. divide by 3 and get each angle must be 60 degrees. So there's an equilateral triangle. And all its side will be the same measure, go with it, A, right? And then we can talk about isosceles triangles. Those are triangles that have two sides equal. So if this is alpha and this is alpha, then that makes this an isosceles triangle, and this will be some other angle, beta. Right? Those are two terms we'll see occasionally. Then, these lead to the following conclusions. I like to do the derivation here. I told you that later on when I went to become a math major, having seen all these proofs really helped me to remember how these things work. And when I got stuck, it wasn't like a foreign language where I didn't know the words. I could figure it out, right? So for instance, suppose I gave you this triangle here, which is an isosceles right triangle, right? Right triangle has a right angle in it. These two angles are equal. Since 90 is here, these two add up to 90. We said they're complementary. So each one is half of 90 if they're going to be equal. We call that a 45, 45, 90 degree triangle. I wonder how its sides compare. Here, they were all equal in an equilateral triangle. What can I do here? Well, if I call this side length A, then by symmetry, right, I can just think of flipping this over on itself. This must also be A, right? And now, what's the length of the last side? Well, by the Pythagorean theorem solved for the last side, this one must be the square root of this side squared plus this side squared, right? Which is the square root of a squared plus a squared is 2a squared. Square root of the product is the product of the square roots for non-negative numbers. So the square root of 2 times square root of a squared is a. Square root of 2a. There's this triangle. It has, let's write it this way, sides a, and square root 2a. This triangle comes up so often in practice if you want to have this concept memorized, excuse me. But every 45, 45, 90 triangle by the similar triangles principle is just a scaled up version of this one. 1, 1, square root 2. You just multiply each side by a and get a square root 2a. So there's the 45, 45, 90 triangle. It always has, it's always just some scaled up version of this. The other one we can do is a 30, 60, 90 triangle. This comes up quite a lot also, right? If I have a right triangle here, and I put 60 degrees here, and so that these two add up to 90, this one must be 30. The 30, 60, 90 triangle has what side length? Again, I want you to memorize these. I think it's worth seeing the proof, even though I won't ask you to prove this on the test. What you do to derive the lengths of this one is you take it and flip it over, make an exact copy over here. So if this is A here, let's say, then this is A here. And then, well, it's an equilateral triangle, right? If this is 2A, then the other sides of the equilateral triangle are both 2A. Now I've got it, because if this is A and this is 2A, I can use the Pythagorean theorem solve for this leg and say, this leg is the square root of the hypotenuse squared, 2A squared, minus the other leg squared, A squared. Well, this is, if you square it out, right, like this here, 2 squared times A squared, you have to square both things, so this is 4A squared, less A squared over here. It's the square root of 3A squared. Again, the square root of the product is the product of the square roots. So you write this as square root of 3 times square root of A squared is A. That's the last side. The one you memorize then is this. Let's write it here. This 30, 60, 90 triangle has side lengths A square root 3A and 2A. And you can say they're all scaled up versions of this one. 1 square root 3 and 2. That's a 30, 60, 90 triangle. It's any multiple of this one. Now that allows you to solve a lot of important triangle problems when you have in construction or whatever one of these cases come up. Suppose I said find the sides of each of these, or I give you a special triangle. I'll say this is a 30, 60, 90 triangle. And suppose this side length is 7. What are the other two sides? Let's do this one. This one is 7. What are the other two side lengths? Well, if 7 is one side, then this side must be, this is A, this must be 2A. It must be 14. And this must be square root 3A. Or square root 3 times 7. And again, we write the whole number first and then the radical. So it's 7 square root 3. So there's the sides of this one. Given that 7 is the one side, the other sides are 7 square root 3 and 14. Right? Suppose I gave you this one. 8. And I want to know these other sides, x and y, in a 45, 45, 90 triangle. What are the other two sides if this side is 8? Well, now what you do is you say, if this is A, then this is square root 2A. So we could call this, instead of X, we call this X instead of A. We could say 8 is square root 2 times X, right? X square root 2X and X. And then this one has to be equal to X also. Since it's a 45, 45, 90 triangle, it's isosceles. Right? So if 8 equals square root 2X, we can solve this by dividing each side by square root 2, and I'll say 8 over square root 2 is equal to X, and that is something off in the test. Why is that something off? Again, I didn't simplify it. Sometimes I'll let you leave radicals on the bottom if it doesn't write in a simpler form, but this one I noticed, if I think about it, 8 is equal to 2 times, well, let's multiply top and bottom by square root 2. Let's write it that way. If we rationalize the denominator, that means get rid of the root of the denominator. By multiplying top and bottom both by the square root 2, now the bottom will be 2, right? I multiply square root 2 times square root 2. So I'm going to get 8 square root 2 over 2. And now 8 over 2 is 4. And I notice I can get rid of the quotient, rewrite this as 4 square root 2. So on the test, I don't want to see this at the end because it's not simplified. You can get rid of the quotient and write it as 4 square root 2. Right? So they're solving these special triangles if you have a 45, 45, 90 or a 30, 60, 90 triangle. You just remember the ratios of those sides. Let's look at one more here.
Why wouldn't the 8 just be like, could you not just half that to get X? Because 8 is 2A and X would be A. Why do you have to go through so many steps?
I did more steps than maybe I have to write in. I'll do a lot of these in my head, but
This is the 45, 45, 90 triangle. So the hypotenuse is square root 2A, not 2A.
Okay.
yeah, I'll go through that. I see what you're saying. Yeah, it's not 2A, it's square root 2A. So, right, thank you.
Okay, that works. Thank you.
Mhm. All right, so here's the harder case. Suppose I give you a right triangle and this side is 5. And I say it's a 30, 60, 90 triangle. What are the other two sides, say X and Y here? Well, if 5 is, referring to the other triangle I wrote on the other board, right? We have 1, A, square root 3A, and 2A, just the 1 square root 3, 2 triangle scaled up. 5 must be then square root 3A, square root 3x, right? So if this is x, this is square root 3x, just replacing a with x. And so I can solve for this side here, I can solve for x by this relationship. And we'll say x is then 5 over square root 3, and this one you can leave like this. I'll mark that as okay on the test. It won't be the answer, however, that's in the back of your handout. Lots of mathematicians leave this like this because it's going to be just as simple to write as the final answer. This one, when I rationalize it, again, you multiply top and bottom by square root 3 to get rid of the radical on the bottom. Same quotient, right? Because I multiplied top and bottom by the same. The bottom is now 3, and the answer on the back of your homework supplement will be 5 square root 3 over 3 if this was in it. And that's not simpler to write than this. So when you can't cancel anything, here you could cancel something. So you want to cancel it and get rid of the quotient. But when nothing cancels, I'll let you write it like that. This is okay. Or this is okay. You can always rationalize. This is what your algebra teacher taught you to do. Why do you have to rationalize? This looks more complicated than this. The reason is that once it's rationalized, the numbers will be equal if they look equal. That if you look at these at first, they don't look equal, right? But if you rationalize this one, you get this one. That's the idea. So if it's simpler to write it this way, I'll let you leave it this way. But to compare it with the answer in the back, you have to rationalize it. But there's this side, that's x, and now a, and now this side has to be twice a or twice x. So y has to be 10 square root 3 over 3, twice this one. So there's a solution to that. Get that off the camera. There's solving those special triangles. Well, that's the review. You want to know the sum of angles theorem. You want to know all this terminology in addition. You want to know the Pythagorean theorem. And you want to know similar triangles theorems. And then you want to be able to apply those to these kind of problems that I gave you. I said the test will be similar to this. If I give you on the first test problems on the geometry review, and I might, then they'll be similar to these ones we did today. Any questions at the last second here? I think we're about out of time. All right, well, feel free to come by my office hours on WebEx, and be happy to meet you and talk about
Yeah, I have a question about the homework.
Yeah.
So you said we have homework every day after class. When is it due?
Yeah, it's not to turn in. I said that way at the beginning, but I said so many things. Yeah, no, the homework's not to turn in. It's to study for the test, which will have similar problems.
Okay, and okay, that's fine. And like the tests are on the syllabus, right? Like the dates.
The dates of the test are all in the syllabus, yeah.
Okay, all right, thank you.
Any other questions? All right, once again, I will upload this in case you missed any parts. I know the first day you're gonna have a lot of technical difficulties. And otherwise, I'll see you on Thursday.
Thank you.
Thank you.
Thank you.
Thank you.